Yeah, that is it. All right, so this is a bit of a follow-on from my talk last year, and I'll provide any context required, hopefully, for that. In terms of our roadmap this year, we've got a bunch of new features coming out for our core engine, the cloud layer, and then the development layer. Specifically, as well as the SQL work we showed last year, we've also got a SPIR-V runtime for basically you can compile your PyTorch directly to SPIR-V. We already had JPEG XL support, but we're adding full HDR support and KTX compressed textures. And we've just launched our Horizons OS support with pass-through on Quest 3, and we have some cool new native camera functions coming in the next little while. And I guess the way I tend to position this stuff is that compared to common runtimes, including .NET, which is, compiled, but it still requires a runtime alongside, that we have better memory management and faster general coding, and we use all these rich frameworks or take advantage of rich frameworks. In terms of a lot of the browser and the browser app frameworks, orders of magnitude better memory management than Chrome. So if you've used, Visual Studio Code or Slack or those tools, which are based on Electron, which is basically a Chromium browser and a wrapper, a lot more efficient. And then in terms of the 3D engines, most of the 3D engines that are out there were designed for games, not for enterprise development. So our platform does all the 3D stuff, but hopefully a lot more performantly.
All right.
Okay.
Yeah, it's not. So these are battery defects using the technology we showed last year. So this is finding ripple defects and very small ripples in a plastic lacquer. You can see it's very reflective and hard to see. Down here we've got an inclusion defect, which is a little bit of dust that gets under the lacquer. And then the next example is a pinhole, which is about 100 microns in diameter, so it's very small. And we can detect those. And these have to be scanned at high speed as you're moving over surfaces. Now, one of the advantages of this is that this is a two-dimensional data set. So even though we're capturing three-dimensional surface information, we're not dealing with that true third dimension when it comes to the data itself. So in this talk, I'm going to be talking specifically about the context for sparsification. So when you have 3D data that is, actually in 3 dimensions, when you have time series data, so you're adding a fourth dimension, and you add simulated generated data or AI extrapolated data, you very quickly get into a situation where you have exponential data growth. If we look at an example, once again, that I showed last year, we extract multiple layers from an image set. So in this case, there's a normal map, there's a specular map, there's a diffuse map. So we're actually adding data all the time. And I couldn't really show this properly last year, but if you can see the white ink, so it's about 20 microns thick, wraps over that little copper trace in the motherboard. So you can see axially huge amounts of detail there in those images. So last year I also showed the Orin Nano. This year it's been rebranded as the Orin Nano Super. So to the point of some other speakers, what's happened to Moore's Law here, essentially it's a really nice, well-performing part, but it has a power threshold. So the whole idea is this runs on a 15-watt TDP. There isn't much more you can do within that power threshold, at least at the moment. And the goal is to take 3D time series data and reduce it significantly, so in the order of 10,000 to 1 million times, to pre-compute things like connectivity and to allow for much faster simulation and analysis. We don't really want quantization and compression, and I'll give you some actual examples of that in a second. So if we look at a voxel data set that we're trying to capture, just a single frame, if it's a short int by a short int by a short int, I don't know why I've written it like that, you'd assume 4 floats per voxel. So if you're storing RGB and maybe an intensity, so you're looking at about 70 terabytes for that. Whereas with the scalable point clouds, you can get away with much smaller data sets. So at a billion volumetric points, you're looking at about 52 gigabytes of memory, and with 1 million volumetric points, which is actually can represent a voxel set like that very, very well. You're looking at about 52 megabytes, which is obviously quite a change. So this is an interesting demonstration. I actually showed the demonstration on the right, but I didn't put it in the proper context. So on the right are 500 Gaussians. This is a two-dimensional example. And on the left is the equivalent number of, well, it's actually 484 because it's 22 by 22, but that's what a bitmap would look like versus a series of fuzzy Gaussians. And so what's interesting about that is that there is a fundamentally, this is a fundamentally more compact representation, in this case, for a 2D image. And then what we showed is you can do that for a 3D scene. So this is the hall here. The technique was essentially to go through the photographs that we took and to optimize a series of fuzzy blobs from multiple angles to represent the external geometry of this room. And I guess what's interesting about that is if we look at the point cloud that's generated, it's way too sparse for normal visualization, so you wouldn't use this as a traditional point cloud. It does keep particularly the high frequency information, which is obviously important, so things like the tables you can see have more detail in them. But that's not something you could show to somebody and someone's going to go, oh, that's the Christchurch Town Hall. But what's interesting about that is those exact points you can see here represented just as points. Here they are represented as 3D objects. So this scene is reproduced, this room we're in, with all the parquet flooring, the reflections, the diffuse lighting and those lights, the sun coming in under the blinds. So all of that information has been captured in that point cloud representation, the sparse, resizable point clouds. And that's at around about 100,000 times reduction in data set compared to something you'd consider a reasonable voxel approximation. But as you can see from this example here, voxels fall apart pretty quickly due to the quantization. But now if we look at 3D data sets that are not solid, so we don't have solid surfaces, we're actually looking at things that are transparent, so we have a different mechanism for composing these 3D structures. So if we look at something like an MRI, we have our scans, we have essentially fully known camera position. There's no need to estimate where the cameras are in the scene. We are manually, mechanically scanning for, in this case, the brain. And what we actually find in looking at MRIs is there's a huge amount of homogeneity between voxels in a scan. And that really what you want to do is preserve the high frequency information, and the areas where the voxels are the same, you'd like to get rid of that information, or you'd like to compress that information. I've got to be careful using that word because compression, I said earlier, isn't what we want. We don't want to convolve information into a representation that we then have to do a bunch of computation to expand the data and get it back out again. We want to fundamentally represent the data in a data structure which is useful to us, that is much more compact. And we don't want to just chop it up into slices and quantize it. The other interesting thing about this process is that we've been able to build levels of detail. So when we take the voxels and we convert them into different these scalable point representations, we can do it at different scales, which might be important for different kinds of simulations, or depending on your point of view in regard to the whole data set. So you may choose to have part of the data set represented more sparsely and part represented in much more detail because you're particularly interested in a particular part of the brain. Another thing that's really interesting is just as we do in image compression, so with JPEG and with JPEG XL with VAR DCT, you can choose higher order distributions rather than just a Gaussian. So you can actually have frequency embedded. The only downside to adding this complexity to the blobs is it does reduce the file size by about another order of magnitude, sort of 10 to 30 times. The challenge is you don't now have isolated bits of information. You do have to convolve these DCTs together to get your final density map. I think one of the really interesting challenges, and we've talked about memory access a lot here, is managing your partitioning of memory. If you're trying to run a simulation, you really want to be able to divide and conquer, spread this across many tasks, and you also want to be able to navigate the data in a logical fashion. So we're using octrees to break down the information. So if you've got a massive scan that's too big for memory, you've got a sensible way of partitioning it for other systems or the same system to trawl through and process. And then one of the really interesting things we've been playing with is using things like KD trees. And the idea here is that you can actually capture the connectivity. So at the moment, if you want to take a voxel map of the brain and you want to flood and find all the bone or find all the grey matter or white matter or different types of tissue that you can identify based on their, say, the frequency of the water emissions or the density of the water. You basically have to do a three-dimensional flood fill looking for, is this voxel next to this voxel? And then how do you even describe that? So the connectivity systems for creating a marching cube external hull are very complicated in their own right. The great thing about this is a very fast pre-processing step because you have so much less data in the first place. So you have as I say, 10,000 to 1 million times less points to consider. But you can actually go through and say, hey, these points, we can see these have the same properties. So these are all grey matter. We can actually connect all these in a connectivity tree. And then it makes it very easy during simulation to go back and pull out essentially this core data. This is a really great paper. This is talking about the idea of tomographic reconstruction, so looking at things like MRIs. And what's interesting is that they've done a really good job at an optimizer which describes this alternative approach. And if I was to describe what you're doing when you're taking a scene like this, you are basically adding those Gaussians together. Whereas you can think of this process as more like averaging the Gaussians, because what you're trying to do is to say if I have two Gaussians that are both brain tissue next to each other, it just forms one big Gaussian. Whereas in this example, if I was trying to reproduce a visual scene, that intersection between the two Gaussians would get darker because you're adding, whereas in this case you're averaging, so it just becomes one bigger homogeneous blob. And then if you wanted to subtract something out of the center of it, you'd have a lower value, you'd put that in the center, and now you can make it hollow. So you can think of this as a way of composing material that you can see, or you understand its properties in terms of its internals. So these are some renders we've done. So this is a torso. So you can see, as you move through the slices, and then we've also got a color representation here. So in this case, that refers, you can see the bone on the right and some of the material around the heart there, and cut through from a different angle. So the great thing about this process is you're optimizing, as I say, for volume, not for surface. And just to once again, I guess, re-emphasize the challenge with things like voxels. So this is a, 8K by 8K by 8K voxel of a human cell or a hollow sphere. And the problem is if you quantize much lower than this, then you'll have holes in your sphere, so you can't test for your holes and so on. Whereas ironically, you could literally model, it's an overly simple example because you've got ellipsoids, but you could literally model that with two Gaussians, where you have your external solid Gaussian, which forms your cell wall, and you have your reduced Gaussian in the center. And you can control in the 13 floats that define these shapes, you can define the edges, how fuzzy they are and how sharp they are. So it's basically the shape of that curve as it relates to the diameter of the ellipsoid. And the particular reason we're working on this is for some really interesting stuff we've been doing around refraction. So the examples I've shown you to date have been using reflection So this is a Hoffman modulation dissection microscope in the top right. So that's what a traditional image would look like. And what they use is a diffuse annular light source. So it's a whole sort of lighting system designed to give you even lighting, such as that you're effectively removing the effect of refraction as much as you can. Whereas this system that we put together, this egg's just hatched out of here, and this one's in the process of hatching. There's a couple on their way. These are 7-day bovine embryos. But what's really interesting is you can pick up, if you're at the right focal plane, things like trophoblast cells, which exist on the outside of the cell wall, and they're used to basically implant in the uterine lining. And you can't normally see them because they're transparent from the perspective of a traditional diffuse light microscope. And then the other great thing about this is it actually builds 3D models of all of the subjects, but it builds them as a 3D stack. So the challenge we had is, do we represent this as voxels, because we are extracting pixel level information, but it's just such an inefficient thing to do, especially when you start getting time series data. You would quickly end up in the terabytes of storage, yet 99% of that is literally empty media surrounding the subject that you're looking at. So this ability to compress this data is incredibly important. I'm not sure if this video playback is going to work. I'll just give it a quick go here. Platypus. This is quite a cool example. I'll pause this temporarily. So this is quite intriguing because we have a sperm just here, and we've also got one here in the zona. So that's made it through to fertilize that egg. And that's not normally information you can see. And I'll just go back to that again. So you can see it's sort of stuck in that space and flicking its tail around. And this, the one down here is actually quite interesting because as the flagella is moving, the flagella varies from 1 micron to about 1/10 of a micron. So yeah, it's in the 100 nanometer range at its tip. So we're picking up a lot more information than we should according to the limit of diffraction. But you can actually see as that tail, as the flagella beats, it's actually rotating the egg on the left-hand side, which is quite hilarious. Now this is interesting. This is showing the 3D reconstruction. So these eggs you can see appear to be rotating in space. Obviously they're not physically being rotated. That's due to the calculation from the light angles. And you can see the diffraction because that's using white light, so you're getting chromatic aberration there as that diffracts at different, or refracts and diffracts at different angles. So what's cool about that is we can actually use those color hues to help with the reconstruction process. In fact, these are being analyzed with multiple LEDs in practice, so we have different frequencies. And with that multispectral information, you can do label-free information, so you can actually tell what's a lipid or what might be a bit of cellular tissue. And I guess that adds up to that same problem with data sets. So your data set just keeps getting bigger and bigger the more metadata you want to pack against each of these useful points. And I guess the thing that really seems interesting to me from a simulation perspective is that you're actually creating this fundamentally new representation that is compact and at different levels of detail, so depending on where you want to drill in and how you want to consider your connectivity, you can retrieve that information very fast. Because in a standard voxel array of a brain, anything you want to do is slow and painful, as you have to get all that data out of memory. You have to troll through it to try and establish these shapes and these values. So particularly when you want to try and perform simulations, or you want to analyze this over time, what we can actually do is to say, I want to keep these Gaussians with an index on them, and I only want to change a Gaussian, or I only want to change one of these blobs over time if there's a significant change event occurring. So you actually get time series encoding on these as well. And that turns out to not just be good for a sparser and a more compact representation, it actually tells you something about what's happening to your simulation. So if you've got things that are bending, or things that are changing temperature, or changing pressure, or whatever's the parameters you're looking at, Essentially, those values can change even if the physical shape stays the same. And then as the physical shape starts to deform, you're essentially getting a delta or a change in the area that is moving. Now, just like a video codec, if the entire scene moves and pans, that there's going to be challenges to keep that encoded. But in a huge amount of microscopy work, you're looking at a subject, and the subject stays roughly in the same field of view, just due to the nature of how microscopes work and their size relative to the subjects. Now, the subjects may move through the scene like a sperm might, but in many cases, you're imaging things like bacterial colonies or maybe a man-made lithography as well. So it could be photonics or lithography where you have something that's just there and needs to be inspected. Cool.